All right, this is the first video for the atoms and heat unit notes. So for this unit, I want you to be able to explain what heat is, discuss how temperature and heat are not the same thing. That one's pretty tricky. For your math, I want you to be able to calculate the efficiency of an engine. So that one can be a little bit of fun. And then finally, I want you to be able to discuss the 4 laws of thermodynamics. All right, so let's get started. Atoms and molecules. Basically, what is heat? So you guys have all done this before. If you rub your hands together, you will notice that they feel warmer. What you're doing basically is you're turning kinetic energy into heat. And you're doing that through friction. Friction is something that converts kinetic energy into heat. That's basically all friction does. It just converts energy into heat. Now, heat is kinetic energy because the kinetic energy of the molecules, so as you take your hands and you rub them together, you're shaking the molecules back and forth, making them move faster. So since the molecules in your hands are moving faster than they were before you rubbed your hands together, they feel warmer. So heat is the shaking of atoms and molecules that is rapid in speed but microscopic in distance. Now, a molecule then is a combination of atoms that stay in a clump. And that's something you should have talked about in chemistry. I'm sure you did. We have basically 3 ways that atoms are held together: covalent bonds, ionic bonds, and metallic bonds. So when molecules break apart, or when they come together, is when we call something a chemical reaction. So, in all materials, the molecules are constantly shaking. But how fast? And this is where it's kind of a coincidence almost. It's about the same as the speed of sound. So that is roughly 700 miles per hour, which is roughly about 1,000 feet per second, which is about 330 meters per second. So all those numbers they're about the same. I'm just changing the units. And there's a reason why the speed of sound is the speed of sound. That's something we're going to come back later. There is a connection between molecular movement and how fast sound travels. So, atoms themselves are way too small to be observed with an ordinary microscope. Roughly, they are about 2 times 10 to the negative 8th centimeters, which equals roughly 2 times 10 to the negative 4th microns. Whoa, let's back up here. I know we're probably familiar with centimeters, but microns. Microns are completely different, aren't they? A micron is the same thing as a micrometer. The unit for micro is mu, and it is 10 to the negative 6th meters. So you can take a look at going from centimeters to micrometers, and it would drop from negative 8 down to negative 4, or I should up to negative 4. But whenever you see the word micron, I spelled it there, a micron is the same thing as a micrometer. Okay, the next thing I want to talk with you about is Brownian motion. I've got a picture of it over here. So here's how it got started. When we started using microscopes, 200-300 years ago, experimenters would see little tiny pieces of dust, like in a fluid, and they would see the pieces of dust move back and forth. So imagine that this piece right here is a piece of dust. You would see it darting back and forth on, let's say if it's floating on a piece like a little bit of water. You'd see it shake back and forth and move all over the place. And they try to make the water as still as possible, make sure there's no air blowing across it, nothing. And they still saw it shaking back and forth. And what this did was it proved that there are, in fact, molecules and atoms, and that they are in a constant state of motion, because the piece of dust is so light that when a molecule hits it, it's able to move that piece of dust. So this Brownian motion, and this is what it's called, this Brownian motion proves the existence of molecules. Well, at the very least, it proves that molecules and atoms are in a constant state of motion. For his first Nobel Prize in physics, Einstein created a model for Brownian motion, and that won him his first Nobel Prize. And what that basically did then is it proved beyond a shadow of a doubt that atoms existed. So, and that wasn't until the mid-1900s. So if you were born before the year 2000, you can officially say that you were born in the century that atoms were proved to exist, beyond a shadow of doubt. And again, that's thanks to Einstein. Okay, speed of sound and speed of light. Here's that connection I was mentioning earlier. Sound can only travel at the same speed of the molecules shaking. And this is because sound travels through a material by making molecules bump into each other. So sound traveling through a gas cannot move faster than the velocity of the individual gas molecules. We call this a compression wave. So over here on the right, I have an example of a speaker pumping out sound. And what the speaker does is it pushes, there's a little diaphragm that pushes back and forth. So think of that diaphragm moving back and forth. It's pushing some molecules together, it's pulling some molecules apart. And that's creating sound waves. Well, if you think about it, the wave then that travels away from that speaker can only travel as fast as the molecules can move themselves. So this is why, molecules move about the same speed as the speed of sound. And it's really because sound can only travel at the same speed as the molecules that are shaking in its medium. All right, so you can measure the speed of sound yourself. So let's say if you know a certain distance is 1,000 feet. Then it should take sound approximately 1 second to reach you. A good example of this is a baseball field. If you go out and, especially if you're going to watch a game, uh, you're about 1,000 feet away from where the batter is. You should see the batter hit the ball, and roughly 1 second later, hear the crack of the ball hitting the bat. Another way to measure the speed of sound is through thunder and lightning. And this is one that you can do during the next thunderstorm. So a good rule of thumb is 5 seconds. So you see the flash of lightning and immediately start counting. If you reach 5 seconds before you hear the thunder, the lightning is roughly 1 mile away. So that's a good way to, figure out how far you are away from a thunderstorm. Now the speed of light is much, much greater. It is 186,000 feet per second, or 300 million meters per second. That's so fast that light can travel around the circumference of the planet about 7 times in 1 second. So it is extremely fast. Computers can take about 1/billionth of a second, a billionth is a nano, to complete a calculation. So in that nanosecond, light travels about 1 foot. And this is why computers have to be small. Basically, the electricity coursing through wires runs at about the speed of light. So the computer needs to be able to retrieve information to do a calculation. So if the information is too far away, it has to waste several cycles to get to it. So let's think about this. If a computer is 1 foot long, or if the hard drive is 1 foot away from the CPU, it takes a nanosecond for the information to travel from the CPU to the hard drive, and then a second nanosecond for it to come back. Now, a nanosecond is very, very short, but it can add up. And so think about here in the school where our servers are several hundreds of feet away. Now you can start to experience some sort of delay between a calculation. That's enough to start to slow down the calculation speed. It's still incredibly fast though. So if at computer speed, now another unit we use is something called a gigahertz. So if the computer speed is 3 gigahertz, then the light goes only 4 inches in 1 cycle. And again, electricity flowing through wires is about the same as the speed of light. So that concludes video 1 for atoms and heat.